Welcome to the neighborhood of a magnetar, the dead star with a grudge. In the grand cosmic hierarchy, most stars die quietly. They fade away like a retired accountant moving to Arizona. But some stars have a bit of a main character syndrome. They go out in a supernova, a blast so bright it outshines entire galaxies. When the dust settles, sometimes what's left behind is a neutron star. Imagine something with more mass than our entire sun crushed down into a ball the size of a small city. Manhattan, but with the weight of 1 billion Titanics. It's dense, it's hot, and it's spinning thousands of times per second like a ballerina who's had 18 espressos. But then there are the 1%ers, the outliers, the divas of the graveyard. About 1 in every 10 neutron stars decides that being the densest object in the universe isn't enough. They want power. Through a process we're still trying to figure out, partly because extreme celestial physics is hard, and partly because these things are terrifying, the magnetic field of the star gets cranked up to 11. Actually, it gets cranked up to about a quadrillion. That is a magnetar. It is a dead star that refuses to stay quiet. It is a magnetic ghost haunting the vacuum of space with a field so intense it literally warps the fabric of reality itself. And the scariest part? We didn't even know they existed until they started screaming at us from the dark. On March 5th, 1979, the universe decided to jump scare us. 2 Soviet space probes, Venera 11 and 12, were cruising past Venus, minding their own business. Suddenly, their radiation detectors hit the ceiling. A wave of gamma rays, the most energetic form of light, slammed into them. Seconds later, it hit NASA's Helios 2, then Pioneer Venus, then Earth. It was a blast of energy so intense it was like someone set off a nuclear flare in our cosmic backyard. The scientists were baffled. It wasn't a normal star. It wasn't a black hole. It was coming from a remnant of a supernova in the Large Magellanic Cloud, a satellite galaxy of our own. For a few milliseconds, this tiny, invisible speck released more energy than our sun does in 150,000 years. Naturally, the scientific community did what it does best. It had a mild existential crisis and spent the next 2 decades arguing about what could possibly possess that much oomph without being a galaxy-eating black hole. To understand why a magnetar is so extra, we have to talk about its magnetic field. We measure magnetic strength in units called Gauss. The Earth's magnetic field? About 0.5 Gauss, enough to wiggle a compass needle so you don't get lost in the woods. A common MRI machine around 10,000 Gauss, strong enough to rip an oxygen tank across a room if you're not careful. A magnetar? 1 quadrillion Gauss. That's a quadrillion. That is a 1 followed by 15 zeros. It's a number so large it ceases to mean anything to the human brain, which is mostly evolved to count how many berries are in a bush. At this level of power, the laws of physics start to look more like suggestions. In a magnetar's field, the vacuum of space itself becomes biringent. That's a fancy science word for saying the empty void acts like a prism, splitting light in 2. If you tried to look at one, the light wouldn't even travel in a straight line. And then there's the star quake. Because a magnetar is spinning and its magnetic field is so tangled, the crust of the star is under immense pressure. Think of it like a cosmic pressure cooker, but the lid is made of solid diamond-density iron and the steam is pure radiation. Eventually, the crust snaps. A starquake of just 1/10 of a millimeter, less than the thickness of a human hair, releases enough energy to trigger a giant flare. In 2004, we caught one of these flares from a magnetar called SGR 1806-20. It was 50,000 light-years away. That's halfway across the galaxy. It was so far away that the light had been traveling since before humans invented the wheel. When that flash hit Earth, it actually physically blinded our X-ray satellites. It partially ionized Earth's upper atmosphere from 50,000 light-years away. Imagine if it had been closer. If a magnetar popped up within 10 light-years of us, it wouldn't just be a bad day. It would strip the ozone layer off our planet like a grape being peeled. We'd be toasted by cosmic rays before we could even finish tweeting about how bright the sky was getting. The universe isn't just big, it's remarkably efficient at finding new ways to delete us. At this point, you're probably thinking, okay, it's a big, scary magnet, I get it, I'll just stay away. But the magnetar doesn't just play by the rules of big, it plays by the rules of the quantum. And that's where things get weird, even for space. In a magnetic field this strong, the vacuum of space itself isn't actually empty. It becomes a thick soup-like medium. This is called vacuum birefringence. Normally, light just goes. It travels through the void at 300,000 kilometers per second, minding its own business. But near a magnetar, the magnetic field is so dense that it actually polarizes the vacuum. Light gets stuck, it gets split, it gets bent into shapes that shouldn't exist. If you were standing near a magnetar, assuming you hadn't already been turned into a human noodle, the stars behind it would look like they were melting into a kaleidoscopic fever dream. And then there's the chemistry, or rather the total destruction of it. Your body is held together by electromagnetic bonds between atoms. You're basically a very organized collection of Lego bricks. But a magnetar's field is so strong that it overrides the internal forces of the atoms themselves. It takes those nice round atoms and crushes them into needles, long, thin cylinders 1,000 times thinner than they are wide. Chemistry as we know it simply stops working. Carbon can't be carbon. Oxygen can't be oxygen. You wouldn't just die, you would literally dissolve into a cloud of subatomic toothpicks. It's nature's way of saying, I liked your structure, but let's try something more linear. It's an environment so hostile that even the most basic building blocks of the universe give up and go home. It makes a black hole look almost hospitable. At least with a black hole, you know where you stand, usually on the event horizon, screaming. But a magnetar? It unmakes you before you even get close enough to touch it. Here's the kicker. We've only found about 30 of these things in our entire galaxy. That sounds like a small number, like a small, exclusive club of cosmic psychos, but those are just the ones we've caught screaming. Because magnetars are active for a very short time, usually only about 10,000 years before their magnetic field decays and they settle down into boring, regular neutron stars. That means there could be millions of dead magnetars drifting through our galaxy, cold, dark, invisible husks of former monsters. We're sailing through a graveyard of sleeping giants, and every now and then, one of them wakes up. One of them snaps its crust. One of them sends a ripple of gamma radiation through the void that hits our little blue marble with the force of 1 trillion suns. And we just watch the satellites flicker. So, where does that leave us? We live on a planet where the biggest magnetic threat is usually just a credit card getting too close to a phone case. We worry about the weather, our Wi-Fi signals, and whether we left the stove on. Meanwhile, out there, hidden in the velvet folds of the Milky Way, is a city-sized ball of dead star stuff that could unmake our entire biological existence without even trying. It's not malice, it's not a villain, it's just physics. Physics with a very dark sense of humor. Magnetars remind us of a truth we usually spend our lives trying to ignore. The universe is not made for us. We are a delicate chemical accident occurring on a damp rock, protected by a magnetic field that is frankly adorable compared to what's happening elsewhere. We are fragile. We are temporary. We are in the face of a quadrillion Gauss, statistically insignificant. But there's a strange beauty in that insignificance, isn't there? The fact that we, creatures made of atoms that would be crushed into needles near a magnetar, can actually understand them. We looked into the dark, saw a flash of light from 50,000 years ago, and figured out the math of the impossible. We are the only part of the universe that can look at a monster and call it by its name. One day, every magnetar in our galaxy will run out of energy. Their fields will decay, their screams will fall silent. They will become cold, dark spheres of iron drifting through a cold, dark universe. and eventually, so will we. But for now, the ghosts are still active. They're still spinning. They're still waiting for their crusts to snap and send another reminder across the void that we are guests in a house we do not own. Sleep tight, and maybe keep your magnets away from your hard drives, just in case.